Alrighty, so we are into Module 3. That's what that says. Module 3 is open. Most everything is there. What is not there, I think, is just the quiz stuff. So I'll try to get working on that. Other than that, I think things are there. And, if you find something appears to be missing, certainly let me know. We'll come back to this and do the alpha game. But let's see. So, let me go back to here. All right. Any questions about anything right now? No, life is great then, I guess. Okay. I'm going to actually do things slightly backward as to what the module has. I'm going to look at a question and see how we would try to determine a reasonable answer to it. And then actually go to a part of the prelude where it suggests playing a particular game. And I find that works probably best in a group. Okay, so I thought, what would be a reasonable question to ask? And, well, this class is mostly nursing biopsychophysiology students. We do have an accounting student. And so, I could say, hey, I have a question. And really I'll end up turning it into a statement, but, are there an equal number of female and male students in those majors? So biology, psychophysiology, psychophysiology. Wow, okay. And accounting. I think that, nursing. I got to have that on there too. So nursing and accounting. Okay, and I use this class as a sample. And I count them up, right? There's 2, 4, 6, 8 of you here. We have 2 more students that aren't here, but I'll count them in the sample. Why not? Okay, and that's 10 students, all female. Okay, so my data. 10 students, all female. So now I'm going to change my question a little bit, sort of put it in terms of a statement. So the way I'm going to try to answer this is I'm going to say, well, assume that's true. So assume there are an equal number, okay, in the population. Okay, so that's what we assume, because that's kind of how my question is based. So now I'm saying, are there an equal number? Well, let's assume there are. Go take some data. Okay, now I take that data, I happen to get a sample of 10 students, and they're all female. Does that mean this can't be true? Well, that's the question. That's the statistical question. Because it is a sample. Because if I ask you right now, right, are there any, do you know of any males in nursing? Yes. Okay, how about any biology majors that are male? Yeah. You know, you meant physiology or psychophysiology. Yeah. Accounting. Sure. So you know there are some. So just because we have 10 students who all happen to be female, it doesn't absolutely at that point negate this possibility. But the question is, okay, from a probability standpoint, statistically, how strong would our argument be against this, given this data? Okay, and the way we're going to answer that through the rest of the whole darn course is we're going to determine, assuming this population, how likely is this sample? Okay, now in this case, it was a little better sample for illustrating this on Tuesday. Because on Tuesday, we actually had 2 male students in here. Okay, because what you tend to do is we'll look at sort of extremes and we'll say, okay, yeah, I got data of 10, 10 female students, but I'm willing to look at data that are even more extreme than that. Okay? And the reason I'm willing to do that is you're really playing these two things against each other. You know, typically the data will appear, at least at face value, to contradict whatever you're assuming here. If it doesn't, don't go any farther with your work. Okay? Because the only reasonable stuff we get out of the statistics is when our data, which should fall in our alternate hypothesis as we look at hypotheses, it should, on the surface, appear to contradict your assumptions here with your null hypothesis, or what we think the population is, okay, or what we're going to assume the population. We may not think the population is this, but we're going to assume it for our question. And so, had it been 10 students, 9 female, 1 male, when we go to count, we would still count 10 students, all female. And the reason is that also when you think about just asking that question, so assume you had an equal number and you went out and you collected data lots and lots of times. If you keep getting data that seem even more extreme than this, which we can't really, again, because we got 100% female, but suppose we had the 80% female, then if I went and collected a bunch of samples and got 90% female, 80% again, 90% again, and so forth, and I was sure it was from an equal population, then each time I got that, I'd kind of go, oh yeah, sure. I guess that's looking more and more possible. So I'm going to count everything out there, and as we go. And so this is the big part of it, though. We're assuming something about the population, and we're going to look at how likely we could get this data. Okay? Oh, and I forgot my coin, and I don't think I have any change. Anybody have like something they could flip? We'll just do it once because you need it. do that. All right. Somebody was ready for the vending machine.
A quarter of
Anything will do. Probably shouldn't trust me. Okay. I forgot those because, you know, typically what I do is I give you each some, you know, I bring in a little disc for each of you to flip. But, you know, these days they frown upon us passing stuff out and that kind of thing. So, so I've got a coin, and the reason a coin will work nicely is I'm going to assume they're an equal number. Oh, it's a coin, heads, tails, right? So then I'm going to sample from my population. This is my population, or at least as I sample from it. And I have 10 observations I'm going to make with, you know, for that sample. And so I'm going to flip the coin. That's either going to mean male or female. Wait, it's your coin. Heads and tails, what do you want to be, you know, male, female?
Heads, female.
Heads, female, tails, male. Okay. So, heads are female. So you flip the coin. I'll probably miss it a few times. Heads. Okay. So, female. And flip it again. That's another person. Oh, female again. I have a two-headed quarter I could have brought in, but didn't do that either. Heads. See, so it's looking like maybe I have a two-headed quarter. Tails. Okay, so there's a male. We do it again. See, and this is where if you each had a coin and we did it, it would be much faster, right? So male, that was tails again. Heads. Okay, getting there. Yep, see. What do we got? Heads. So another female. You know, and it's interesting so far, right? It's kind of looking like, well, lots of females showing up. Not that weird. Another heads. Another heads. This is awesome, actually. And another heads. Wow. Okay, after class, I am going to buy a lottery ticket. Okie doke. So, okay, I do this, I get the data, 8 female, 2 male. So does this seem to support that, right? You know, I mean, I don't know. Even if I'd gotten 10, I don't know. How lucky am I, right? It's not clear what this means. Okay, so really, to get an idea of how likely this is, I probably need to do this a bunch of times. You know, how many is a bunch? 1,000. Let's do it 1,000 times. You know, maybe 10,000. We'll stick with 1,000. Okay, do it like 1,000 times, and we can look there and count it up. Okay, I need the quarterback. No, not really. I'm just scaring you that I'm going to stand up here and do 10,000 flips, right? That's where technology comes in. Okay, so in your project, see, what you're doing is instead of, well, and in your case, you're going to have an unfair coin for your project. But here, you know, we've got something that would take a fair coin. And what I want to do is do the same sort of thing with the spreadsheet, but like 10,000 times. Or sorry, not, well, yeah, 10,000 flips, but a thousand times. Now, I know that if I can put some headings here, and I'm going to make these narrower. Why is that so slow, I wonder? Let's see, column width, I'll make that like maybe 0.3 inches, and that way we can see things a little better. And I'm going to need my null hypothesis, which we usually call P0 for proportions, and I'm going to assume that that is equal to 0.5. Okay, equal number. And then I'm going to sample from that population. Let's see, I'll skip a space here, and 1, 2, and once I get the 1 and 2, I can highlight that and grab it and pull it over. There are my 10 students, 1 through 10. And then now, to simulate flipping the coin, all I really need to do, one way would be I could do a rand between. We saw that earlier. I could do something like rand between, whoops, 0 and 1. And the reason I would use 0 and 1 is if, now I'll have to decide what a 1 is and what a 0 is, but whatever a 1 is, however many across there, all I have to do is add up the row, and that'll tell me how many I got if I use zeros and ones. So the 1 will be maybe like the heads or like the tails. It doesn't really matter. We just need to know at some point. But so I could do that and then fill in across with that. Now the thing is, that's really only good if it's a 50-50 chance. Okay, but you see, there I've got some heads and tails, whatever those are. We'll have to figure that out, but okay, that would work. But I'm not going to use that because in ours, we aren't going to have 50-50. So we got to do something just a little more sophisticated. And what we'll do is we'll generate a number between 0 and 1. So fractions, so it just is a number between 0 and 1. And then if it is 0.5 or less, we'll call it a heads or a female or whatever. And if it's a greater than 0.5, so between 0.5 and 1, we'll call it the other one, the tails, the male, whatever. We'll do zeros and ones. And so that just starts, to generate a random number, I just say rand and put some parentheses with it. That generates a random number between 0 and 1. So if I hit enter, I got 0.1. Now it's actually probably 0.13 something or 0.08 something. It's just rounding it because it's short. And then, but now I have to make it into a 0 or a 1, and that's where we use that if idea. And so if my random number is less than or equal, okay, so I just less than or equal, I need a condition. Less than or equal to, and I'm going to click on that B1 because that's where my 0.5 is. And then I need dollar signs on that. Now, if you're using Excel, actually, if you hit the F4 key, it will add dollar signs. And if you keep hitting it, it will add various combinations of dollar signs. But we need the dollar signs on the B1 because as I copy this thing, I need it to always look exactly at cell B1. And so I have that. That's my condition. And then if it is that condition, we'll call that a 1. And if it's not, we'll call it a 0. Now,
because it's 50-50, it really didn't matter if I called one a 0 and, if I switched them. But if that had been like 0.6, then that would have really mattered, which one got the 1 and which one got the 0. So I do that, I hit enter, and it gave me a 0, and if I grab that and pull it that way, I get a bunch of 0s and 1s. Okay, so there are my flips of my coins, and we'll assume that the 1s are females. Okay, partly because, well, we got 10 females, so it'd be nice to know how often we got 10. And so now I need to do this a total of 1,000 times. Now, in this case, since I've only used one row, I know I need to go down to row 1001, but I could always put extra numbers in a column here from 1 to 1,000 to tell me where to stop. But I'll just grab that and pull it way down and just keep going until I hit 1001. One more. Okay, and there we go. Just like that, I've done 10,000 flips. That's what's nice about the technology. Works well that way. And now what I want to do is just sum these up. And so I could write up here, this is the sum. This isn't exactly how I'm having you do it in the project, but it gives us the idea of what's going on. And so now I'm going to sum these up. So I'll say equals sum, and highlight that from D. Well, I don't know if it's letting me do D, so I'll just close that off and then go back in there and type a D. I made my columns too narrow, so it was having trouble. And so I can make that a little wider. And now, if I double click on the bottom right here, it'll just fill in all the way down. Well, if I double click, there we go. And notice it changed. I had an 8 up there, now it's a 3. It's going to do that with the RAND command in most spreadsheets, maybe not all. But every time I click and do stuff, it's going to change the numbers. But that's okay, they're random. And so now I have all those. And what I'd like to know is, out of those 1,000 times, how many times did I get 10? Okay, and well, so I could just start scrolling down and trying to keep track. That would be bad. And so here I will just put, greater than 10, or greater than 10, no, equal to 10. And again, if we'd had 8, I would check 8, 9, or 10. Okay, as far out as I need to. But now I'm just going to check, and I'll say equals. Now the way I can do this is I can count the number of cells that meet a particular condition, and that's this thing called count if. I don't think I have you use count if in the project. I have you actually create a frequency table. But for time, I'm just going to do a count if. Now the range, so I go here, and I know I go down to 1001, so I got to the 10 there, and so I'm just going to add a 0 and a 1, and then comma. And next, I need the criteria. And I wasn't sure how on Tuesday, I kind of had an idea. I wasn't exactly sure what I needed to do, and I might have forgotten by now already. But, Google or something like that. You can go to Google and say, hey, you put in the word Excel and what you need. And what I might put in is like count if in this case. How many of you watched Sesame Street growing up? 1, 2, 3? Oh, come on, all of you did, didn't you? But there, isn't there the count? Who likes to count? You know, so, anyway. That was a long time ago, yeah. So I think it took, I had to put it in double quotes, my condition, and what I want to know is whether it's equal to 10. Okay, and then put that in double quotes like that, and close that off, and hit enter and see what happens. 1. 1 in 1,000. And that number will probably change if I, say I type a 3 and hit enter. See it change to 0. Again, in Excel, you can do, I think, an F9 and it will recalculate. Mine doesn't do that. Goes back to 1 again. So it's a really small number. It's like 1 in 1,000, 0 in 1,000, something like that. Okay. Oh, up to 2. Nice. So what's that tell us? Right? So what we've just done by doing this is, for the hypothesis test, P0 is equal to 0.5, and the alternate, we're going to say that P0 is greater than 0.5. This is called a one-sided test. For that hypothesis test, now there are a lot of, when you're doing proportions and so forth, the letter P comes up a lot. Okay? So our data, we came up with 10 out of 10. P0, I didn't mention what that was, right? P0, the proportion of females. Okay, if I don't tell you what P0 is, it's kind of hard to decide what I've done. Okay, so that's the proportion of females in the majors. Our data, 10 out of 10 or 1. Okay, well that definitely fits this as opposed to that. But the question is, well, is this convincing enough evidence to decide the answer must be this? Okay? And, well, what I can tell you is we have, and this is called P hat. Like I say, a lot of letter P flying around here. But then that probability that we came up with, well, it fluctuates. But I'm going to say it's about 1 out of 1,000. Right? We ran this experiment 1,000 times. Looks like it was about 1 in 1,000. Okay? The latest one I have is 2, but we had some zeros, we had some ones. I'll call it 1 in 1,000. So here's what we did. We said, okay, we'll assume this is true. We will actually go sample a population where this is true. And we'll sample that population, a sample size of 10, but then we'll do it over and over 1,000 times. And well, if we do it 1,000 times, it turned out only one of those times comes up with our data, or sort of worse. Now, in our case, we couldn't do any more than a 1, but so just 1 in 1,000 times. So the question is, well, do we believe then that we ought to choose this as the true thing? Okay? And our answer in this class is no, we shouldn't. We should choose this one. Okay, and the reason is that probability, what we call a p-value, the probability that I could actually get data like this is only 1 in 1,000. It's really small. And we're going to say, no, if it's that small, then probably we aren't that lucky. In other words, the reason we got 10 was because actually there's a higher proportion than half. Okay, that's what we would say with this sample. Now, Tuesday's sample, we had 8 out of 10. If I go in here and I change this, instead of being equal to 10, if I make it greater than or equal to 8, that's what we had on Tuesday for our sample. And I think we had 10 people again there. I think it was 8 out of 10. If I hit enter, we get 61. And again, that'll fluctuate a little bit. But 61, so this number is 0.001. 61, just if we had that, 61 out of 1,000 is 0.061. If that was our sample, which it happened to be on Tuesday, we would say, oh, now, we don't have enough evidence to refute that, and so we'll stick with it. Okay? The only difference, right? The only difference was our data and then how likely that data happened to be. Everything else is the same. It's the same idea. And so, it all depended on our data and what we got for that likelihood. Okay? And the question is, well, why is this okay for the null hypothesis? Why is it that that's not enough evidence to contradict that claim, but that is? Right? It seems actually kind of arbitrary. I mean, where do you put it? Well, in this class, we put it at 5%. So a p-value greater than 0.05, we're going to go with our null hypothesis H0. Now, does it mean we really think it's true? No, not necessarily. It just means we don't have enough evidence to decide it's wrong. Okay, that's all we're really saying, is we don't have enough evidence to say it's wrong. And if we have a p-value less than 0.05, then we go with our alternate hypothesis. We say, that, the chance of us getting these data is small enough that we don't think we must have been sampling from that population. It must have been a different population. Okay? We don't know what, right? We don't know exactly what that population is. We just don't think it's that population. And that's the rest of the course. We spend our time looking at, if we're doing a particular type of study with particular type of variables, how do we end up with that p-value? How do we calculate it? What are we looking for? But the bottom line is almost always the same. Is it bigger than 0.05 or smaller than 0.05? And that's our threshold. Now, why that threshold? Well, that's our game. Now, this has a short video at the beginning of it. Speakers aren't real loud, but People seem to say they could hear it yesterday. So we'll put that on. Less than 3 minutes.
When we run a hypothesis test, we use a significance level to determine whether the p-value is sufficiently small to reject the null hypothesis, h0. We often use a threshold of alpha equals 0.05. But is there something special about the value 0.05? No. At least there's something special about the precise value of 0.05. But there are reasons why a number near 0.05 tends to be reasonable. Let's run a little experiment. We have several scatter plots based on samples from different populations. For each scatter plot, your job is to weigh two possibilities. There is no upward, linear trend in the data. Any trend we observe is simply the result of chance selection from the population. This is the null hypothesis. There is an upward, linear trend in the data. That is, any trend we observe is the result of a real trend in the population, not just that the sample happened to show a trend. This is the alternative hypothesis. Strong evidence for the alternative hypothesis would come in the form of an unambiguous linear trend up and to the right. To help you get started, let's cover a few examples. In this first example, we can observe an upward linear trend. Most people would say that this trend is unambiguous and probably evident in the population represented by the sample. That is, the trend in the sample data in this case seems so clear that most people would conclude that there is probably some real trend in the population, and they would reject the null hypothesis. In the second example, it's unclear if there's an upward linear trend. In this case, we will not reject the null hypothesis. In this last example, it looks like there might be an upward linear trend. Some people might say yes, that trend seems so strong that it wouldn't happen from chance alone, so reject the null hypothesis. Other people might be more skeptical and decide they cannot confidently reject the null hypothesis. In this case, it's unclear which we should go with. Your decision might be different than those of your classmates. Many of the plots that you will be presented with may seem like they could go one way or the other. Generally, if you can't confidently reject the null hypothesis, we suggest you do not reject the null hypothesis. One last word. There are no correct answers, and your choices are not being graded in any way. So just do your best to decide whether the upward linear trend is so strong that the null hypothesis should be rejected for each plot.
Okay, so they give us a bunch of plots here. I need to make it, I guess, a little smaller yet. There we go. They give us a bunch of different plots, and we're supposed to choose, okay, clear upward trend or uncertain. You know, we just think it looks like random data. We don't think there's anything going on there. And we'll do it democratically, but what I'll do is I'll go around, and each of you you'll get a chance to, you'll decide, and then we'll just see if everybody agrees or not. If they don't worry about it. If they do, yeah, you're still not that special. Okay, so, yeah. Okay, Natalie, what do you think on the first one?
B, or the second option.
Right, no upward trend, you're saying. Okay, so how many agree with Natalie? Everybody see? So that was easy. Okay. All right. Chloe? No trend. How many agree with Chloe? No trend. Does everybody agree? Yeah, it looks like everybody's agreeing. Unanimous so far. Okay. Serenity, what do you think on that one?
I was still saying no trend.
You're going to go with no trend? How many agree with serenity on that one? Maybe, you say. How many want to go with a trend, an upward trend? Okay, we'll go with upward trend. All right, and Teresa's not here, so Sydney, what do you think on this one?
I'd say there's an upward trend.
An upward trend, okay. So how many agree with upward trend? 1, 2, 3, 4, 5. Okay, so, yep, we're going with upward trend. And Katie?
I'm gonna say it's uncertain.
Uncertain, okay? So, how many going with uncertain? Most of you, okay? But we were a bit uncertain about that, so makes sense. Okay, let's see, where are we? Alexis, what do you think?
No trend.
No trend. How many agree with Alexis? 1, 2, 3, yeah, okay. No trend. And Kaylin, what do you think? You think there's an upward trend? Okay. So how many agree with Kaylin? 1, 2, 3, 4. Yeah, okay. Yep. So upward trend. And Colleen, what do you think? No trend? Okay. How many agree with no trend? Looks good. Okay, no trend. And we are back to Natalie. What do you think?
No trend.
No trend? How many agree with no trend? No. How many want to go with trend? Upward trend? You got to vote. Let's see, 1, 2, 3. You're going with upward trend? Sure. Okay. So I think that made it. Actually, we might have had a tie on that. Maybe I should have gone with no trend because it was a tie, right? You know, so, all right. That was Chloe. So Serenity, what do you think? No trend? How many want to go with no trend? Yeah, okay. No trend. And Sydney, what do you think? No trend. How many want to go with no trend on that one? Okay, looks like no trend. And where were we? That was Serenity? No. Who did we just do? Did we just do you, Serenity? No. See, Sydney, we did, yeah. So back to Katie. That's where we are.
I say upward.
Upward trend. How many want to go with upward trend? Okay, looks like upward trend. And Alexis, what do you think?
Upward trend.
Upward trend. How many want to go with upward trend? 1, 2, 3. Yeah, okay. So we're going upward trend. We're getting toward the end, I think. Kaylin, what do you think? No trend. How many want to go with no trend? Okay. And Carlene, what do you think? No trend. How many want to go with no trend? Yeah. Okay. And there we have it calculated. Now I won't go through. That's what we came up with. Those are the p-values beside them. You all, it's interesting. This is probably about where I would tend to fall, I find. I've done this myself a few times, and they're always different and random. So these are the p-values. 0.01 is the top. Now what we had was, I should probably use the mouse pointer here. What we had this 1 in here where we said no trend, but I guess consistent-wise, we either should have picked that one as a trend or picked the next one as no trend. And what's kind of nice, you can come down here and actually look at the different plots. And that one we said as no trend, and this one we said as a trend. They look pretty similar in the fact that, you know, we shifted one or the other. So either you could say this class was somewhere around a 6% or a 10%, depending on how you decided we should have gone on those two that were next to each other. So we as a class, at worst, we are saying, at least for these kind of numerical data and that kind of thing, we should, instead of going for 0.05, we should probably go with 0.10. Oh, okay. Or maybe 0.06, because, again, that's where we were a little different, was in that 0.06 to 0.1 range, and we didn't do enough of them to really tell. It was interesting, Tuesday's class, they had none, all their trends were together, all their no trends were together, and their splitting point was exactly at 0.05. I have never had that happen in a class before. It's just kind of weird, It's like, oh, well, we'll just use that one from now on and say, yes, it has to be 0.05, right? But no, that's not exactly true, but it's in that range somewhere. Okay, if you look at numerical data and scatter plots like this, to try to decide there's a dependency, and that's what's going on, is if there's an upward trend, there seems to be a dependency. And we would say, oh, we think there is a dependency when we see an upward trend, but we're assuming, the assumption is it's coming from a population in which there is no dependency. And so we're going to say, oh yeah, now that's wrong. There really is a dependency when we are somewhere around that 0.05 value. Well, actually less than the 0.05 value. Okay, and looking at this yourselves, hopefully that kind of gives you some intuition as to why, yeah, sure, that's a reasonable number. Is it a perfect number? No. But it's a reasonable number. And so that's where this comes from, or at least partly where it comes from, and why it is indeed an okay number, at least for the type of studies we tend to worry about in a class like this. Okay. Any other questions? Anything before we go? Nope. Okay, well, I will see you on Thursday then.